Okay, I'll make that past. Our next talk is John Chu from the University of Technology in Sydney, and he'll be telling us a bit more about experimenting with rewriting systems. Thanks, John.
Thank you, Lawrence. Hello, everyone, and welcome to my talk about experimenting with writing systems. This talk is about my project supervised by Professor Murray Elder, also at UTS, whose talk you just attended. And this will consist of 3 parts. First, I'll describe the programs or routines for writing systems that I have written in Python. The second is about a pattern in single cycle writing systems that we have gotten from experimenting with those routines. And the last one is represent a conjecture for single writing systems from the pattern that we have observed. Okay, so just a refresh. So before we dive in, we go through quickly the definitions of writing systems again. So a writing system is a pair S-T, where S is a non-empty set, also called the alphabet, and T is a set of rewriting rules, LR, where LR are words made from elements in S. So we write A reduces to B if A is of the form ULB and B of the form URB, and LR is in the rewriting rule set. So for example, the set S comprises of 2 elements, A, small a and large A, and T with 2 rules. So A reduces to lambda, and large A small a also reduces to lambda. So lambda is the empty symbol. So the reflexive and transitive closure of the reduce operation is denoted with the arrow with the star above, reduces to, and reflexive, transitive, and symmetric closure of the reduction operation is called equivalent, denoted with 2 headers and of representatives is well defined on the set of those equivalence classes, and hence makes the monoid M presented by the writing system as T. And when the equivalent class of every letter has an inverse, the monoid M is a group, and we say it is the group presented by the writing system as T. Okay. So some interesting properties for a writing system is finite if both S and T are finite sets. This length reducing if for all rules in a writing rule set, we have that the length of the left-hand side is larger than the length of the right-hand side. A writing system is terminating or Noetherian if there are no infinite sequences of allowable factor replacements. It is confluent if whenever W reduces to X and W reduces to I, then there exists another word Z in such that X and Y both reduce to Z. And the writing system is convergent if it is terminating and confluent. And our writing system is inverse closed if every element in the alphabet, monoid, has an inverse. Right, so now we move on to the motivation of the project here. So the problem of finding algebraic characterizations for families of groups can be presented by families of writing systems, which has been brought to attention since the late 1970s, has proven very challenging. And in 1978, Mahlener and Otto, in an effort to solve this problem, have made the following conjecture. So let G be a group, and G admits presentation by a finite convergent length reducing writing system ST if and only if G is plane. So the plane group is a free product of finitely many free groups and just groups. So the goal of the program for the project is to prove the conjecture for inverse closed finite convergent length reducing writing systems. Hereby we can shorten it to ICFC LRRS. So with alphabet of sizes 2 and 3, or find a counterexample to the conjecture. And the reason that we only we set our target only on alphabet of sizes 2 and 3 is because the limitation of the computing power that we have, which will prove to be a big problem, as we'll see later on. And so to approach this, we can use theorem 4 from Alan Pickett's paper, which was previously presented. So we can, using this theorem, we can decide if a group presented by an IC, FC, LRRS is plane. So on the theorem, if G is a group presented by an inverse closed, finite, convergent, length reducing writing system, then the following are equivalent. So G is plane. Any non-trivial finite order element in G is contained in a unique maximal finite subgroup of G. And the relation is transitive on the set of non-trivial finite order elements in G. And the relation is transitive on the set of non-trivial finite order elements in G of geodesic length with respect to S of length at most 11 RT plus 1. So we'll focus on the first and fourth statements. So G is plane is equivalent to the transitivity of the relation on the set of non-trivial finite order elements with a bound of at most 11 RT plus 1. And so on theorem self-writing system confluent, and we need to compute the order of the elements in the writing system. So how we approach this? So there are some previous words that we can make use of to find out if a writing system is confluent and is normalized, and to compute the order of an element. So from Newman's lemma, a terminating writing system is confluent if and only if it is locally confluent. So what is the difference between confluent and locally confluent? So we have confluent if whenever W leads to X and W leads to Y, that's confluent. But for local confluence, we need only one step. So for example, this is two symbol here. It can denote one to many steps. With local confluence, we just need one, so an immediate. So we can just apply one routing rule W to obtain, and if we obtain two different words, then by local confluence, they have to converge onto unique same elements. Okay, so that's Newman's lemma. We can use local confluence to easily check for confluence and reduces computation time. And so next we have normalized. So this is also a definition from Adler and Pickett's paper. So a writing system ST is normalized if on any rule LR, the right-hand side R is irreducible. Every proper subword of the left-hand side is also irreducible. And if a left-hand side is presented two more times in the writing rule set and implies and reduced to R and R prime, then it implies the two left-hand sides are the same. And ST has irreducible letters if each letter in S is irreducible. So we note that if a writing system, the writing system ST is an inverse closed finite convergent length reducing writing system that is not normalized, then there exist subsets of the sets S and T such that the new writing system is a normalized one. And moreover, it can be computed from the original writing system So therefore, without loss of generality, we can assume that any inverse closed finite convergent length reducing writing system considered is normalized with so and when it's, and you have the and every rule has either the form maybe reduces to lambda, or in which case the group is presented is a free product of the cyclic groups, or and we have the length of the left hand side is exactly one letter longer than the length of the right hand side. And so now we come to the final requirement, which is the computation of the order of an element. So on this, we can use Narendran and Otto's polynomial time algorithm, which was published in 1988. And so basically, the algorithm has an input a writing system that's such that and that presents a group and a word in that writing system. And so it finds for all reduced cyclic permutations of the word you, and it finds out if such cyclic permutations is a prefix of any left-hand side of the writing system. And we have to run this algorithm on input t and u to the power k for each k in, sorry, it's supposed to be u to the power k for each k from 1 up until the total length of the left-hand side, or the left-hand side of the writing system plus 1. And so now we move on to the routines for the writing systems. So within Python, this routine can accomplish 4 tasks. So it can generate a writing system from a seed word, and check if the writing system is confluent using Newman's lemma. You can check if the writing system is normalized, and you can compute the order of an element with Narendran and Otto's algorithm. And it must be noted that this writing system is currently written to work with single cycle systems, which we have an example following. So for example, we have a seed word of the string AB. So from that one, so since the writing system is inverse closed, we have the alphabet, small a, small b, and the inverses of a and b, so large A and large B. And the single cycle means that if the group presented by this writing system has this Cayley graph. So if you move follow the sequence here, and you can see the writing rules here. So we have the inverse closed rules. We have the rules AB, which is this this point. Then you can also go through this route. So go opposite in the opposite direction. So you have capital A, capital B, capital A, and so on. So these are the alphabet and writing rules for this writing system, single cycle writing system. So we have the routines ready. However, we have soon encountered the challenge when we're doing a trial run. So even with small alphabets and RT, or the length of the right-hand side values, the total number of elements to be generated and checked for transitivity is already impractical. So with an algorithm of size 2 and left and right-hand side of length 3, number of words to be generated alone is sum 4 times 3 to the power of I, with I from 1 to 19. So in total, we have to generate close to 7 billion words, and this is not accounting for the process we have to check the order of each word. We were So we changed the direction of the project a bit, and we have found another problem that a major contributing factor to the difficulty in solving Maliner-Otto's conjecture is a scarcity of samples of interesting writing systems that present groups. So the following is one of the few examples available to us of finite convergent length reducing writing systems with alphabet S with 3 letters A, B, X, and their inverses, and those writing rules. This is also a single cycle writing systems, and it contains, so it's of the form where you have ABX repeated 3 times as the seed word. And so when we were experimenting with our routines, we wanted to find out all the writing systems that have alphabet of sizes 2 and 3 with seed word of length 7, 9, 11, and so on. And we want to find out which inverse closed finite convergent length reducing writing system that we can get from the alphabet and of the seed word of so we have found that for 2-letter alphabets, the only seed words that generate writing systems that we can find is of the form just 1 letter and repeated for the length of the seed word, and for the alphabets of size 3, so 3 letters, we have also those writing systems, and we have, interestingly, we have a sequence. We can divide it into a sequence of all 3 letters and repeat it for a number of times. So, for example, this one here, you can see it is the sequence A, B, C, repeated 3 times, C, A, B, repeated 3 times, and so on. So, and of course, this example is among those that we have. So from this one, we have made a conjecture that writing system ST is convergent and normalized if and only if the seed word W is of the form x1 to x cubed to the power of r, where q, r are both odd numbers, and xi is in the alphabet S for, and I energize that implies that each letter is different from each other. So basically each sequence x1 to x cubed here is composed of unique letters that no letter can appear twice in the sequence. And moreover, if the seed word W is of this form and the writing system ST presents a plane group, so meaning that the Maliner and Otto conjecture holds for all single cycle writing systems in that form. And currently, we have proven this in one direction. So we have proven that if the seed word is of the form x1 to x cubed to the power of r, then the writing system generated from the seed word is convergent and normalized, and it presents a plane group. And the proof is since the time is limited, I'm running out of time, I think. So I'll just talk about the proof for normalized. So if we go back to the definition of normalized, we have for any rule LR, and the right-hand side is irreducible. This is true for the writing systems because all our writing rules have the length of the left-hand side is exactly 1 letter longer than the length of the right-hand side. So, which means no right-hand side can be reduced, and every proper subword of else is also irreducible, since this, so every proper subword would be shorter than the length of any left-hand side. And since the sequence are composed of unique letters and no letter appears twice in any sequence, this condition here, so LR and LR prime implies R equals R prime is also satisfied. And so that's the proof for normalized. And for convergence, since it's a bit more involved and we have running out of time, I'll not be talking about that. And finally, then the writing system that is generated by this C word W presents a plane group. And this can be proven using Tsetse transformations. So the group presented by the writing system ST has the abstract presentation. We have generators x1 to xp, and W reaches the sequence x1 to xp to the power of r is equal to 1.
Sorry to interrupt, John, it's time to start wrapping up, I'm afraid.
Can I finish this, or?
Depends how long it takes, but please do,
yeah, we will be quick. So we can perform Tsetse transformation by adding a new generator y equals x1 to this one is xp. Or this gives since we can add a generator that can be expressed as a word in the original generators. We can add this word y here, and so basically y is equal to w, so y to the power I is also equal 1. And we have the additional y here in the generators. And next we form another Tsetse transformation to remove the letter xi to get the presentation x1 to xp without I. So xi has been removed, and the relation here which contains xi has to be removed. And this presentation is isomorphic to the group presented by the free group of rank 3p-1 and product with the cyclic group of rank r. That's the end of my talk. Thank you for listening.